All right, so we're in 8 point, no, we are in 7.5 today. So we're looking at a couple work problems for calculus. So the first one we're going to look at is Hooke's law. So Hooke's law says, if we're talking about a spring constant, we're stretching a spring, how much work is it going to take to do that? So say our formula is proportional. So it says our force is proportional to our distance. So for Hooke's law. So say it tells us that it's going to take me 18 foot-pounds of work to stretch a spring 4 inches from its original height, or original position. So it's 18, so our work is 18 foot-pounds to stretch a spring, 4 inches from the original, or from its natural position. Okay, so this is in feet, this is in inches. So problem, we want to change this to feet because our answer is in feet. So 4 inches is 1 foot. Let's convert that in 12 inches. That's 1/3 of a foot. Okay, so our formula is 18. We're going to integrate, so from 0 to 1/3. So we're going to stretch it from its original to 1/3 of a foot. Now, we're looking at this formula. So k times our distance. We're just going to use x because we like x as our distance. Or we could use d, but then we've got dd, and that's kind of confusing. So we're going to use x. So we're going to integrate this and then solve for k. Because we want to know, oh, no, we didn't. I didn't tell you what we want to know. It gives us this information, and it says, well, how much work to stretch an additional 3 inches. Additional, let's see if I can spell 3 inches. Okay, so first thing we need to know is, well, what is our constant here? So we're going to solve for k. So we're going to integrate this. So it's x squared over 2 from 0 to 1/3. Okay, so let's see, if I plug that in, if I plug in 1/3, get k over 2 times 1/3 squared minus k over 2 times 0 squared. So that's going to give me 18 equals k over 18. So k is 18 squared, which is 324. All right, so now we're going to integrate it. So we're going to integrate 324x dx. Now we want to know how much work it's going to take to stretch an additional 3 inches. We don't really care. We know how much work it's going to take to stretch the first 4, but to stretch it an additional 3, we're going to start where we stopped here. So we're going to start at 1/3. And then additional 3 inches would be 7 out of 12. That doesn't reduce, so we're going to say 7 out of 12. Okay, so let's integrate this. 1/3, 7/12. So 324 over 2. We've got 7/12 squared minus 1/3 squared. And I'm going to plug that into a calculator. I don't want to try to figure that out. And I end up with 37.125 foot-pounds. Okay, so notice that it only took 18 foot-pounds to stretch it 4 inches, but that next 3, it took double that. So the more it's stretching, the more tension there is. So it's gonna be harder to stretch it the further you go. That's how we would find that. Now, if it already gave us, if it just gives us a force, let's see. No, we're good. So here we've got this. That's what we're looking for. So let's look at another one. So say we've got, it says, Neglecting air resistance and the weight of the propellant. Okay? Determine the work done in propelling a 5-ton satellite to the height of 100 miles above Earth. Okay, so if we're looking at gravity, dealing with the weight of something being propelled from Earth, because I know you do that on a regular basis, our formula, I'm joking, is C over x squared. Okay, so our force is this constant over x squared, and we could use K. The book uses C over x squared, so it's inversely proportional. So this force, so our weight here, what we're looking at, we said was 5 tons. So we're taking something 5 tons, and we're going to propel it above the Earth. Now, it's 5 tons on Earth. Okay, so we're kind of working against gravity, or working with gravity. And if it's on Earth, how far is it from the center? Well, it's 4,000. We're going to use 4,000. It's approximately 4,000 miles from the center of the Earth. So the radius of the Earth, we're going to say, is 4,000 miles. So C here is 5 times 4,000 squared. And again, let's plug that into our calculator. And we end up with 80, 0, there we go. A bunch of zeros. Okay, so if we're going to take this thing and we're going to propel it 100 miles above Earth. Okay, so we're going to look at this. This is our constant. So we're starting on the Earth's surface, so it's 4,000 miles from the center. We're going to go 100 miles above it. So we're going to go to 4,100. So now I've got this 80 million, I can't seem to think this morning, over x squared. And we're going to integrate that. So this is, I'm going to go ahead and rewrite that and make it a little easier to work with. X to the negative 1. No, negative 2. Not negative 1 yet. So when we integrate it, we're going to add 1 to it. So now it's x to the negative 1. X to the negative 1. So let's go ahead and move that down and divide by negative 1. So we'll stick a negative there. I don't need my negative 1 now. So if I plug this in, I have too many zeros. We've got negative 80 over 40 minus a negative. And if we plug that into our calculator, I get 487.8. And that's miles, tons. So miles, tons. Okay. Oh, and I completely lost you off the screen. Okay, so if we're dealing with gravity, this is the formula we're using. If you're stretching a spring, we're talking about our force equals K times our distance. Okay, so let's do one more example, and that is water. Okay, so say we've got, let's see, let me read the problem. It says we've got a water well that has an 8-inch casing